Okay, nice. Hi everyone. We'll be doing this lecture will be a continuation to Shreya's class on intro to linear algebra. Just a quick recap. So, what all did we do in Shreya's class? Okay, we defined something called vector space. These are the main objects that we'll be studying. So, what is a vector space? Vector space V is always defined over a field. It's usually denoted by capital V, a field is usually denoted by F, and it satisfies some stuff. So usually when you think of a vector space, maybe a good example to keep in your mind is if it seems too intimidating, is something like Rn or yeah, or Qn. So it's list vectors, uh, the set of all vectors of some fixed size. That's a good example to keep in mind. So again, this field is where you can add, multiply, and divide, subtract, and divide nicely. And that's a field in short. And a vector space over F is where you can add two vectors, but multiplication of two vectors doesn't fully make sense. Instead, you can have a scalar multiplication, meaning there should be a well-defined thing for multiplying a vector v and v lambda and f, then lambda v should also be in v. That's the main idea. That's the main things that a vector space should satisfy. Okay, and what else? We also looked at isomorphisms, homomorphisms. These are basically ways in which uh, we can compare sort of two uh, two vector spaces. So for example, consider okay. Oh yeah. Okay. So let's say we have something like we want to somehow maybe you have two different um, vector spaces in and somehow you want to show that okay they're essentially the same thing, they're very identical. So the way you do that is you show to show that they're isomorphic to each other. Or okay, so what is an isomorphism or a homomorphism between two vector spaces? More formally, it's then you can have a function, say phi, between v and let's say w, such that you want some things to be satisfied, like phi of v1 plus v2 should be equal to phi of v1 plus phi of v2, and phi of lambda v1 should be equal to lambda times phi of v1. Let's say both of these are over f, then lambda from f, v1 from v, v1, v2 from v. So such a phi is called a homomorphism, or also known as a linear map. And an isomorphism is just when phi is bijective. So this is a homomorphism, and uh, homomorphism plus phi bijective is just an isomorphism, right? So this is something we defined. And another thing to recall is we looked at the basis of a vector space and proved some nice things about it. So what is a basis? A basis is essentially okay. So before that, a basis is essentially a set of vectors that are linearly independent, that are linearly independent and span. So a basis of V So when the span is equal to okay. Would you want me to go over any of these definitions, or is this okay?
Just linearly
So far.
independent.
Okay, we say that a set of vectors is linearly independent when basically, okay, let's say V1 to Vn. This set is linearly independent when none of these VIs can be written as a combination of the others. So for example, if we can write V1 as some A2 V2 plus A3 V3 plus AN Vn, then these are not linearly independent. Because you can get V1 as a combination of the other things. So V1 is sort of dependent on the other vectors.
Okay.
Or a more formal definition of this is the only solution to A1 V1 plus A2 V2 up till AN Vn is equal to 0 is only solution to this is when all AIs is equal to 0. Notice that these are all coming from the field and these are all vectors. The VIs are vectors and the coefficients are coming from the field.
Got it.
So for example, consider the set of all vectors in R2, right? Or consider all the two tuples. So a very standard basis that usually is considered for that is 1 comma 0. Sorry, this is 0 comma 1. 0 comma 1 and 1 comma 0. You can, if you want, these two vectors are linearly independent because you cannot get one as a, you cannot scale one of them to get the other one, right? If you scale this guy, then you'll get this y-axis. If you scale this guy, you'll get this x-axis. So they are linearly independent and they also span the entirety of R2. Because if you want to get any vector a comma b, it's just a times 1 comma 0 plus b times 0 comma 1. So this is the basis. In fact, if you have any two linearly independent vectors, they will form a basis. So for example, let's say you take 1 comma 2 and 2 comma 1. They also form a basis because you can, if you want to write any a comma b, can somebody do the algebra for me? I just took this example up right now. What do we write for something times 1 comma 2 plus something times 2 comma 1. In terms of A and B, you can get some, you can actually do the algebra for this. So since it's x and y, then you would want x plus 2y to be equal to A and 2x plus y to be equal to B. And there is a solution on x and y for this. X plus y is A plus B, so y is minus B and so this, okay.
Y is 2a minus b by 3.
Oh, really? Oh, yes, sorry, my bad. I can't. Yeah, 3x plus 3, x plus y is a plus b by 3. So y
2a
is a
minus b by
minus.
3.
Yes.
Yeah, just 2a. And it's similarly
And
access to b minus a by 3.
yeah. So indeed, you can write any vector as a linear combination of 1 comma 2 and 2 comma 1. But I also similarly observed that if you have, let's say, two vectors that are not linearly independent, so let's say 1 comma 5 and minus 2 comma minus 10, then the only things you can get from the combination of these two is just multiples of 1 comma 5. Since this is a multiple of 1 comma 5, this is a multiple of 1 comma 5, the only vectors you can get as a combination of these two is just multiples of 1 comma 5. So basically you will only get that this line. You won't get the entire plane. A basis is where you should get the entire vector space. Okay, so this is not a basis. And also basis should have the nearly independent things. So this is not in fact spanning. I would say this does not span R2. Okay. So a nice claim you can try to work out and like do the algebra and all later is any two linearly independent vectors in R2 span R2, meaning they form a basis. Okay. But I think this should intuitively make sense, right? Because all we're doing is just like solving linear equations and just solve them and they'll have a solution. If you try to do the same thing over here, then you won't get a solution. Okay? Some silly exercise you can try working out later. Okay. Is the notion of a basis and linear independence and stuff, does it make sense?
Yes.
Okay, thanks. I see something in the chat. Okay, yes. All right. Okay, so now we can move on. So last time we did some nice things. We proved that a basis is something that is, so again, some last recaps and everything. We showed that it is something, okay, by definition, basis is something that's linearly independent and spanning. But we also showed that it is something that is something that is maximally linearly independent. That's also equivalent to saying it's minimally spanning. And that's also equivalent to another nice fact, which is that every vector in our vector space has a unique representation uh, in terms of elements of the basis, in terms of vectors, the linear combination of vectors in the basis. Right?
What do you mean by maximally and linearly independent?
It basically means that you cannot, any other vector you add to our set, it will become linearly dependent immediately.
Oh, okay.
Yeah, so note that it's not saying maximum, then in that case it would be the set with the largest cardinality, which is linearly independent. But like as it turns out, that is in fact the same as saying maximal here, but the important part is that over here it's maximally, which means that you cannot add anything more to it to make it and still have it be linearly independent. Right? Okay, so these were some things that we ended off with in the last class. Okay, any questions or anything about any of these things? Okay. All right. So how about okay, are there any more conjectures you can make about the basis? Just based on this example of R2, is there anything else you can say? Which kind of seems silly, but still why is it not enough? Okay, Shreyan in chat is saying maximum linearly independent is not enough for a basis though, as a linear independent with maximum cardinality. Yeah, we are yet to show that. So as it turns out, okay, so maybe I should just reveal that any basically, okay, are there any conjectures before I say this? What about in R2, can I have a basis of size 3?
No.
Right. So can we make a conjecture about the size of the basis, or if we consider all the bases, is there a conjecture that we can make about
A
that?
degree of some sort? I have no idea.
like, okay, maybe we are overthinking this. So all I want to say is that every basis will have the same cardinality. Does it intuitively make sense? Yes, okay, this
yeah.
feels like something that should ideally happen in a nice universe.
Can you say you need n bases in Rn? Like the cardinality of the basis will be n.
Yes, sure. So why can we say that?
Like for each coordinate, you have one basis, so n that way.
Sure. Yes. So assuming this is true, assuming so this okay, this in fact it turns out that this is indeed true. And this fixed cardinality is also known as the dimension of the vector space. So this cardinality is also called the dimension of the vector space. Okay. And okay, so there is something that Sriyan has put in the chat, which also we'll probably not be addressing in today's classes. Vector spaces with infinite dimensions. So we will mostly only be looking at vector spaces with finite dimension today. And what I mean by that, okay, so since we have properly not yet concluded the existence of a dimension, I will just define, I'll say if there exists a finite set W such that a W spans, okay, this I will say, this like angular brackets I will say is like span, like the span of all these vectors in W is equal to V. Then I will say, then this is a definition. V is finite dimensional. Okay, this is how I will define it. And mostly we'll only be looking at finite dimensional things. There are some cool infinite dimensional thing, like infinite. Can somebody give me a nice example of an infinite dimensional vector space? It is like not just R raised to cardinality of n or something. Can you think of any infinite dimensional vector space?
R over Q.
Sorry, say that again.
R over Q would be an infinite dimensional vector space.
Yes, sure, true. R over Q. Yes. I was also thinking of this like a set of polynomials, Rx or something that also works. Like R is a vector space with the field as Q. Okay. Yeah, nice. We will mostly not be looking at this. We'll only be concerned with finite dimensionals for today. Okay. So now I'm saying this is okay. This theorem in fact does hold true for infinite dimensional vector spaces as well. But for now, let's just restrict it to for finite. We'll try to prove it for finite dimensional vector spaces. Okay. Okay. I hope the claim is clear. Now we can try to prove the claim. Cool. Okay. All right. So, any idea? So we're saying, yeah. So any ideas for where to start? What's a good starting point?
A basis is maximally linearly independent. So if there were two bases with different cardinality, maybe we'll have an extra vector. But since the
That's a good
basis,
idea. So proof by contradiction. So assume for the sake of contradiction, that's what this is short for, that there exists B1 and B2, which are both bases. Let's call this something B1, B2 up until VM. And let's say W1, V goes with N, I feel like. And W1, W2, till WM are both what is the what's the plural of basis? Bases? Basises? I don't know.
Put some-
Basis of V. And also let's assume M greater than N, right? Okay. Okay, this is a good starting point. What could we do next?
We can write W1, W2, WM all as what do you say? Are all linearly dependent on V1, V2, Vn since it's a spanning set.
Right, so all of the WIs can be written as a linear combination of VIs. Okay. So let's start somewhere. So we know we can write W1 as some combination, say summation AI VI, I from 1 to N. What can we do with this? So the idea is to somehow maybe change the bases in some way to get some sort of a contradiction, maybe make them smaller in some way, something along those lines. That is what we will be trying to do. What is something we can do with these?
If we know each of the W's can be represented as a linear combination of the V's, then like we can form n W's independently, and for the remaining, can we try and show we can use those n W's to get the other W's as a form of them?
That makes sense. So what Arham is saying is for n of the WIs we can write them as linear combinations of the VIs. And then from there can we show that the remaining WIs can be written as a linear combination of the WIs. Okay. For now, let's only what if we only restrict ourselves to so that's a good idea. Only restrict yourself to W1, W2, WN, let's say. Can all the VIs lie in? Yes, that's a good point. So aren't bases minimally spanning? Note that it's not minimum spanning, it's minimally spanning. So there's a difference between minimum and minimal. The same as what I said between maximal and maximum. So minimum is when the size, the cardinality is the absolute smallest, And minimal is when you cannot remove anything from it. So a minimally spanning thing is when you cannot remove, if you remove even one vector out of it, it will not be spanning anymore. That's all it's saying. Okay. Does that make sense? Okay, Shreyan has also put a nice thing inside. Yeah, this was also my idea. So we have W1, W2, Wn. Now, these n, what can you say about these n? These n things? Can all of these Vi lie in the span of these n things?
No, because we assumed that it wasn't possible. Like assume that the basis is max. So like if we remove any of the Wi's, like it won't be a basis.
Exactly. So if we only consider this set, we cannot, there has to be, okay, I'll just remove this. We don't need this. Okay. We cannot have, exactly. So, cannot, so there should exist some Vi which is not in the span of W. I'm defining W as just the first n vectors in this. And we cannot have all the VIs in this. Because if all the VIs belonged to the span of W, then we could span, then W will also span the entirety of the vector space. Right? Because if we can write VIs, so if we could consider any vector in V, we can write it as some C1 V1 plus C2 V2, and we know up until Cn Vn. But we know each of these VIs, we can write it as some linear combination of the Ws. So we can get V as a linear combination of these Ws. So if all of the VIs from B1 belonged to the span of W, then that would immediately tell us that W spans B. And that would be a contradiction because B2 we are assuming is minimally spanning. Right? Yeah. Is this okay? Wait, Arham, does this make sense?
Yeah.
Okay, good. Okay. Swear, thanks. What happened? I clicked something. Okay. Okay, so now what can we do? What is like the next natural thing to do? There is some Vi which is not in the span. So let's without loss of generality, say it's V1. So what do we do? What can we do? What's the next thing we can do with this W and this V1? So what do we know? So we know that W. What do we know about W union V1 now?
It should be a base. It may be a basis. I mean, it depends on how close M and N are.
It will be linearly independent for sure, though, right?
Yeah.
Why is that? Because we know W is already linearly independent, and V1 is something that is not in the span of W, which means V1 cannot be written as a linear combination of the Wi. So we can just add W safely. I mean, we can add V1 to W safely without contradicting the linear independence. Is that okay?
Yes.
Okay. What can we do next? what if, okay, there was something Nishant had mentioned that, okay, Nishant mentioned that, okay, this could be a basis of V. If W union V1 is a basis, then we sort of have a smaller condition than what we started with, right? Initially, we had two things which were like N and M. Now we have something that is like, something that is size N, which is a basis, and we have something that is size N plus 1, and that's a basis. So we're ending up with a smaller numbers than those we started off with. So that's a good sign, right? If we're starting off with something and we are ending up with small things, we can probably just use like some well-ordering principle on something or an induction of some sort to finish the argument. So if this were a basis, then we are happy. If this were a basis, then we are happy because we ended up with a smaller thing. Because we ended up with a smaller thing than we started off with. Okay, so let's say it's not a basis. Yes, exactly. Nishant has a nice idea. If it's not a basis, then what can we say? Nishant, do you want to speak up and tell your idea? So
Then there's
say
probably some other VI also, which
not a basis.
is linear, which when added to this union will also make it linearly independent.
Exactly. The stress is that, so let's call this set as like W1 or something. Like, this is bad notation because I want a small WI. We'll call it like W1. This is also horrible notation. No. What should I call it? I will call it suggest some good notation. I don't know. Let it just be W and V1, I guess. They say not a basis, then we can. And so there exists another VI, let's say V2 without loss of generality, such that V2 is not in the span of W union V1. We can call it X1. So it's not in the span of X1. Right? Because if all of the VIs were in the span of X1, then this would have been a basis. Right? Same idea as earlier. So then again we can add V2. So then again let X2 be X1 union V2. X2 is linearly independent. And that makes us happy because does somebody want to say why that's happy?
Then we can just like keep on going on till this ends, like we get a basis.
Yes.
That will only be till n minus 1, right? Like we can't add all the VIs. We can only add till Vn minus 1.
Yeah. So we can stop when we get a basis. So sure, at some point we will have to stop because we can't keep on adding things forever. At some point we must get a basis, and then like when do we like if we stop somewhere in the middle, we are happy because again we are ending up with two smaller things, right? So we're starting off with M and N, and we're ending up with something less than M and N. So we're ending up with two smaller things. So that's happy. But what happens if we keep on doing this for a very long time? Then
What if we
what
just end
do
up
we
with
end up with?
M? What if we just end up with M numbers?
We end up with
WN.
W union B1, right?
So we have like V1, V2 until some point, some VI, let's say. And And we have another thing which is like V1, V2, Vi up until Vn. So we get that these two are like spanning the same thing. Right? So the span of both of these things we are claiming is the same. Now can you like see a way to make these numbers smaller? Can we say that can we say that we can exactly. So we can just sort of we can say that W1 to Wn, the span of this is the same as span of everything from Vi plus 1 to Vn. Right? And now these are smaller numbers, so we are happy. Wait, is this, can we go from here to here? Yeah, I think this does make sense.
It would. Why should we be able to? Like, I get it. That's linearly independent, but
Yeah, this is something I came up with while walking today morning. So yeah, this last step is indeed kind of sus. Let me think.
I have a question in X2 is linearly independent. Like we know that
Huh?
W is linearly independent and X1 is linearly independent, but how do we know that some combination of V2 and some other combination of elements from X1 can't form another element in X1?
Okay. So we know that V2 is not in the span of X, right? Sorry,
Right,
X1. So if V2, we already, and we know X1 is linearly independent already.
correct.
So we can just add V2 to X1 and it won't um disturb the linear independence of
But what
X1.
if V2 and some other elements in X1 can form an element in X1?
Okay, sure. Okay, we can just do that algebra and figure it out. So let's say like you're saying there's some element in, okay, let's call it some X, which is like V2 times something C plus some X1 C1 plus the dot some XK CK.
Yeah.
Now what we can do is sort of just rearrange and say V2C is equal to X minus X1C1 to the dot minus XKCK and then divide throughout by V2. So those are equivalent statements.
Oh, right.
And so the reason we can divide is because it's a field. So division and everything all makes sense. Assuming V2 is
Wait, the way
sorry,
I got it
other
is
way, other way around, other way around, other way around.
you divide by C, right?
Yeah.
So V2 can be formed by Xi's, but we know that's not possible.
Yeah.
Okay.
Also, for the steps you mentioned,
Sorry.
also for this step where you go from span of V1
Yeah.
to Vn, for that step, if instead of W1 we had W1 plus V1, even then the spans would be the same.
this is
Yes.
this
But
step is
the
wrong.
span of W1
Right?
to
Yeah, yeah,
W1
yeah.
and
I
it's
mean
not the
we
same.
can this step is wrong because you can just have something like 1, 1 and 1, 2 or 1, 1 and 1, 3. Remove 1, 1 from both of them, they have different spans. The dimension of span is same. So we can use this to define dimension inductively if that's what you're aiming for. But if we are doing
But this is not true. Yeah.
I mean, but you can always just define dimension inductively if you do. Like you can define the dimension works for smaller cases, and since it works
Yeah.
for smaller cases, it works for larger cases.
Yeah. Okay.
But I think it would be
Okay.
much easier if we just did it ulta. Like if we just said we can write V1 in terms of VW1 to Vn and the VW1 to VWN, right? And if we just say we have V1 to Vn is linearly independent, W1 to Wn is linearly independent, right?
So you're saying we can write Wi as a span of the Vi's and
right.
for the first 10 things, and then
And then we can just write V's in terms of W's. Like we can just write V1, V2, Vn union W1, and that is not linearly independent. Right? Okay, and then we can just remove something other than W1. You can remove like one of the other stuff can be removed, and we can just keep on doing this until we change V1, W, Vn to W1, Wn, right? And that would be
that's a nice idea. Yes, that's a nice idea. Yeah.
I mean, I think that would be simpler then.
Yes. That's the one I had seen also. But this is something I thought of randomly, and I was like, this is something I have not seen, but it makes sense that it doesn't work though. Okay.
I mean,
nice.
it could work if you do it inductively, right? If you say it works for dimension.
You
works
don't
for
have to
smaller
explicitly. Okay. Yeah.
So like you
Right.
assume dimension works till size n comma I n minus 1 comma n minus 1 and show it works for n comma something higher.
Let's also just quickly go through what the other things Shrey answered. So we have V1, V2, dot Vn, and W1, W2, dot W1, dot Wm. Okay, and now what we want to do is again, there's some similar idea I want to use. So we claim that okay, we can swap some two of these elements, and this will still be a basis, something like this. Right? And why is this true? Why can we do this? Because you can write okay, maybe somebody else wants to say. Why can we sort of swap two elements and have both of the things still be a basis?
Didn't I just tell now we can just first we put in W1 and then we remove V1. Don't swap. That way it becomes obvious why it works.
Okay, maybe it's like say it out formally so everybody's. Yeah, okay, so what we're doing is firstly we add W1, that's indeed a better way to look at it. And now we know that this is not linearly independent, right? Because W1 can be written as a linear combination of these things.
So now we have some set some linear thingy which goes to 0, which has coefficients that are not 0 at some place. And at least two of these coefficients are not 0, right? Because if only one coefficient was not 0, that means that thing will be 0, and that's obviously impossible.
Yeah.
Right. So you have two of these numbers are not 0, so that we can. So that means one of them might be 1W1, right? The other one, we can just take the other one that can be represented in terms of other things.
Yes. So now we know that this is not linearly independent, which means we can write so this has some non-trivial solution, right? And what can we say about C over here? Yeah, exactly. C is not 0.
And something else is also not 0. That's also
Yes. C is not 0 and some other AI is not 0. So we can just sort of so let's say without a generality, let's say 1 is the one which is not 0. right? So we can remove V1. And now this will now be linearly independent.
It will not necessarily be linearly independent. It just not still span V.
Panic, yes, my bad.
It's a,
Wait, I understood what Shreyan's idea is differently. So, we can represent like the way I understood was like you can represent all the W1 to WM in forms of V1 to Vn,
yes.
and you can represent all the V1 to Vn in forms of W1 to Wm.
Yes.
And since multiplication is the word distributive? Is distributive, right? So since it's distributive, like
Huh?
if you just like move you can just like substitute all those linear combinations of W1 back into the V1s, and you can get that what's the last one? Wm is some linear combination of W1s with till W, what, m minus 1s?
Yes. W1 to M.
So,
Yeah.
so that's the way I understood it. So
Yeah, and then you can keep sort of switching these things and get a contradiction.
wait, no, we don't need to switch it, right? We just proved that it's Wm is dependent on the rest, so that means it can't be a basis.
Yeah, I mean that's how we get that from switching. Now we get V1 to Vn in terms of W1 to Wn by the switching method.
Okay,
Yeah.
fine.
And then you keep switching, and at the end you will get something like W1 to Wn is spanning. But that's a contradiction because we assume that W1 to Wm, which is like a bigger set than this, is minimally spanning. This is the standard thing that I have also seen. Make sense, yes. Okay. So sort of the idea is to replace or switch these things. And okay, so idea is okay. V2, Vn, W1 is still spanning. Then again keep repeating to get W1, W2, Wn spanning. Contradictions. The minimality of the second basis.
I didn't get the
Okay.
idea. Like, why would that above set still span R?
Because see, so do you agree that this set is still spanning? This set is still spanning V. I mean, with V1.
No, that
With V1, it's
yeah.
That's simply because we're just adding W1 to the set. But now what
Right.
is happening is, since this set is already spanning, but removing V1 is not making a difference because V1 is sort of linearly dependent on these other things. So V1 we can write it as a linear combination of V2 up until Vn and W1. So earlier, in this case, whatever we were writing it, let's say some V as a combination of V1 to all of these things, we can just eliminate V1 by writing it as a linear combination of these remaining things.
Oh, in the below equation, you take it to the right side and divide by minus A1.
Exactly.
Okay.
So any number you can write as a linear combination of things in V2, Vn, and W1. And you keep on doing this. Yeah. Okay. Nice. Yeah, so this is like a very neat idea of sort of extending a basis. Another nice thing you can do is like, okay, this is an idea that we were trying to also use earlier is start with any linearly independent set, any linearly independent set can be extended to form a basis. Yeah, this is it's a nice idea that's used a bunch of times. And yeah, so this also proves okay, so now we've just proved the dimension, the existence of dimension in a vector space, a finite dimensional vector space. Quite neat. So this leads us to the one of the main results I wanted to discuss today, called the Rank-nullity theorem. Something in the chat. Oh, does this work for infinite dimensional as well? Wait, let me think. Sure. I guess so. Yeah. What will be the issue that will come? I guess there will be some issue that will come with like maybe some axiom of choice thing that you have to do. Some such thing that comes up where you're like choosing a thing from an infinite set and stuff.
Wait, you are saying that if, I mean, you mean by infinite dimensions that like one basis is infinite dimension and like the other one is finite, right?
I'm bored of infinite.
No, so one finite, one infinite is fine. That is not an issue, I think. But if both of them are infinite, we have to argue they have the same cardinality.
Wait,
Yeah.
what?
Um,
Wait, you are arguing that infiniteness has the same cardinality.
Yes.
that's like a lecture for another time. So there's like a cool thing where you can do where you can properly define cardinality of infinite things. So there's like different kinds of infinities. For example, maybe I'll just quickly talk about it in like 90 seconds. Turns out natural numbers and integers have the same cardinality. This is called the countability. You would think that there's much more integers than natural numbers, but actually they're the same. How about rationals? I mean, clearly there's infinitely many rational numbers between any two integers. So they're clearly like much more rationals than integers. But they also, as it turns out, have the same infinity as naturals and integers. How about reals? Like, okay, now, like, surely you would think that Q and Z, there's the same relation as R and Q or something. But as it turns out, R is actually, you can show that R is strictly greater than the infinity of Q. I'm being very vague just to like blow your mind or something, but there's an actual like way to define the cardinality of infinite things. And there's a big open question also in terms of this. So it's saying, is there an infinity that's like between Q and R? We don't know of any infinity which is like between these two things. And we can't even prove the non-existence of it. We haven't been able to, I think, so far. But yeah, that's like a cool stuff that for another day. But yeah, that's what we want to show with infinite things. Maybe we can come back to this towards the end. Let's do this nice thing. This has like a similar idea of this basis extension thing. So rank-nullity theorem states that okay, let T be a linear map or a homomorphism between, let's say, from vector space V to W. Then the rank-nullity theorem states that the rank of T plus the plus I think the size of the kernel, so the dimension of the kernel of T is the same as dimension of V. The rank of T is just the dimension of image of T. So some side note, definition, rank is dimension, rank of T is dimension of image of T. Just to recap, kernel of T is set of all vectors Vi such that T of Vi maps to the 0 and W. That's what kernel is. Yeah, I think everything else is well defined in this. Okay. So one way to see this is just using the first isomorphism theorem that Shreya discussed in last class. I think that's quite neat and very straightforward as such. There's another nice proof I want to discuss, which I like. So, okay, first of all, is a statement fine?
No, I didn't really get it.
Okay. So what we're saying is, okay, let's say T is some linear map between, which takes in vectors from V and spits out vectors in W. Then what we're saying is, okay, consider the image of T. So you could have, so the image of T also be, okay, before we actually do this, let's, there's some non-trivial things like why should the image of T be a vector space? So firstly, is the image of T just restricted to this will also be a vector space. I think Shreya did this in her class. Then the kernel of T will also be some vector space. Image of T is just basically the set of all this set of all T of Vi, where Vi is from V. And that's the image of T. This is basically going to be some subspace of W. Yes, good point. Nullity is the dimension of the kernel. That's called nullity. This is why it's called Rank-nullity. Not exactly the codomain because we could have maybe V doesn't map to all. Maybe this is not surjective. If T is not surjective, then everything in W is not getting mapped to, right? It's like a subspace of the codomain.
All right.
Okay. So this is quite a cool statement. So let's try to prove this. Okay, first of all, let's just to recap linear maps. Linear maps are very nice. If you know T of V1 and T of V2, then you can find T of V1 plus V2. And if you know T of V1, then you can find T of lambda V1 also. So these are like the main things that linear maps satisfy. Now, why are these nice? So is there anything nice you can say that
Can we consider
about?
can we consider a basis of kernel
Exactly.
and extend that to a basis of V, and we can show that the extended vector basis is equal to the other one, and then we are done.
Yes. So the next thing to look at is like if you know where every basis vector of V is going, then T is entirely defined. That's like a very nice observation to have. So let's say you have some basis of V. Let's say V is spanned by V1, V2, Vn, and these are all linearly independent, then if you know where each of these vectors are going with respect to t under t, then you know where every single vector in V is going. Simply because the niceness of linear map T is like if you, let's say you know that T of V1 is going somewhere, T of V2 something. If you want to find, you know that any vector in V can be uniquely represented as some linear combination, A1, V1, A2, V2, plus up until A and Vn. But T of this thing is just T of A1, V1 plus by the additive condition A2, V2 up until T of A and Vn.
Theorem under condition, we can just
Yeah.
take
Yeah,
Wait,
we
by,
can take the scalars out. Huh.
by this, do you mean like if we take a matrix on R, like R square, if we transform R square by some matrix, then where the initial I hat and j hat go, like where they go, the image of them, by those two image vectors, we can define the transformed thing.
Yes. Okay. So that's a good point. Actually, I want you to discuss that as well. Should I do it right now or should I do it after rank-nullity? Okay. So the thing I want you to say is you consider the space. Consider all possible linear maps between vector spaces between V and W. Now, insanely cool thing is that this itself is a vector space. So like, okay, maybe take a second to appreciate this. When I first saw this, I was like very happy because what you're doing is you have two vector spaces V and W. You're considering the set of all linear maps between these two things. And the set of these linear maps, the set of these functions itself is a vector space.
So you're saying that the set of these functions follows commutativity, the distribution,
Yeah.
and it has inverse and stuff.
No, inverse is not there
I
in
mean,
the
sorry.
definition of vectors. Yeah, like
Scalar.
the two main things is basically like
Scalar multiplication will
yeah.
still lie.
Yeah, over the same field. The field is not changing throughout. So okay, so how am I defining things? Okay, I'm saying that okay, if I have two things t1, t2, I'm going to say the function t1 plus t2. It takes anything v1 as whatever t1 will take v1 and wherever t2 will take v1. And I'm going to say lambda t1 should also be some another function, right? I'm just going to define it as this like multiply by lambda. Why did I write lambda? Just multiply p1 of p1 by lambda, and that's going to be your function lambda 1 t1, and the function t1 plus t2 I'm going to define as the function that adds these two things. And now there's some more details to figure out here, like maybe I'll leave it as an quick exercise. Show these are linear maps. And as in, so that T1 plus T2 is a linear map, and so that lambda T1 is a linear map. But yeah, yes, it's if you define it this way, then this is like finished. It's like it tells you that this is a vector space. Okay. Yes, true. So it's a nice exercise is try to calculate dimension of this vector space. Okay. So quite neat. And the cool thing is that each of these TIs is in fact, so this is something I think Arham mentioned is that each of these TIs is sort of, you can think of them as matrices. That's where matrices come from. maybe we can talk more about this in some time. So it's quite cool stuff. Let's try to complete this theorem. Okay. Yeah, okay, maybe just one last comment I have to make, like for those of you who know what matrices are and what matrix multiplication is. So in matrix multiplication, when you see it, seems quite random, but it starts to make more sense when you look at it this way, because if you have two linear maps, T1 and T2, then you can, let's say T1 is from V to W, and T2 is from W to some other W prime. Then my claim is that T1 composes in T2, meaning you take something, you take an input, wait, T2 composes in T1. Meaning you take an input from V, T1 will spit out something from W, then give that as an input to T2 and spit out something in W prime. In fact, this also turns out to be a linear map from V to W prime. And this is exactly what corresponds to the matrix multiplication. We'll come back to this later, but it's quite cool stuff. Okay. Anyways, so yeah. So now what were we talking about? Yes, wherever all these basis vectors go, completely defines the linear map. Okay. So now what do we want to do? We want to show that the dimension of the image of T plus the dimension of kernel of P is the same as the dimension of V. So let's say the kernel of T is something V1 to V2 up until Vk. So let's say kernel of T is equal to this. So what does this mean? This just means that we have T of all of these Vi. Okay, maybe like I'll say this is the basis of kernel of T. So let's say this. Because kernel of T itself is also a vector space, so there'll be some basis. So let's say it is V1 up until Vk. Okay. Wait, something is going on in the chat. Okay, I'm gonna come to it later. Yeah. So let's say the basis of kernel of T is V1 up till Vk. Now the idea is to add a bunch of things to it to make it a basis of V. That's the idea. And then we will show that whatever things that we add, they are going to be basis of for the image of T. Something like that is our idea. Right, so we can also say, okay, basis of image of T is, let's say, some things like W1 up until WL. Now I want to show that the dimension of V is K plus L. How do we do that?
We can't use these exact vectors, right?
No, because W1 to WL are vectors from the image of T, meaning they're from W. And these VIs are from, not from, VIs are from B. Or maybe we can, sort of this, we can start off with the basis of V, let's say. There has to be some basis of V, right? Which is basically obtained by extending these things. Let's say we get Vk and Vk plus 1 up until Vn. This is much neater. Now, can we do things like this? No? Now, what is it that you want to show? You want to show that the dimension of image of T is 10 minus P. So, what is like a nice thing that will be very nice if true? So we know that, okay, this under T maps to 0, this under T maps to 0, this under T maps to 0, and this under T maps to something, all of these under T maps to something. So what's like a nice claim to make at this point? If we want to show that this dimension of image of T is n minus k, then what's a, can you make a claim? So the claim is that T of Vk plus 1 up until T of Vn form a basis for image of T. Huh?
One minute.
Yeah, sure.
If the transformed VKs like form a basis for the image of T, can we like undo the transformation and say the VKs form a basis for T? Like, is that something allowed?
Undo is not something you can always do, right? I mean, again, like everything might not have a pre-image, and also it's like for that T would have to be a isomorphism, like it would have to be a bijection. Then only you can sort of undo the thing, define an inverse. But
Right.
this is not necessarily a bijection. In fact, if the kernel is non-trivial, then it is not, and then you cannot in fact inverse it.
Okay.
So using Vk plus 1 till Vn, we could like form all the should we say zero? Non-zero, whatever, vectors? Or is that the terminology? So we
Okay.
can form all non-zero vectors, am I right?
What do you mean? Like
That
all
means
all non-zero vectors in which space?
I think we're talking about V, right? So V,
Okay, so you're saying you can form any vector using in V from Vk plus 1 to Vn?
which is not zero.
No. The basis of V is V1 to Vn. So you can form any vector using a linear combination of V1 to Vn.
But V1, V2 like are all like what? VK are like
They're
zero.
not zero. They're
I mean,
not
the
they're not
kernel,
identically zero. They map to zero under T.
they map
Like
to zero. Okay.
T of V1 is equal to 0. Like T of these things is equal to 0.
Oh, wait, T of these things is equal to zero then. So you take some vector which is like alpha 1, V1, alpha 2, V2, whatever. And then you look at its transformation.
So look at T of V. What
And
is
then
that
you
going to
just
be?
find that it's alpha 1 into. So like from V1 to Vk, the transformations will become 0.
Yeah.
And then for Vk
So-
plus 1 to Vn, we get the T of V. So that means that's the basis.
Yeah, that's the idea. So you're going from k plus 1 to n because the rest of the things are mapping
It
to
just
0.
becomes 0.
So you
Yeah.
have this. So you have T of V, T of any V, you can write as a linear combination of Vk plus 1 to Vn.
Yes.
And this
we
is
know the
also unique
cardinality.
because the alpha is a unique, so over here also the alpha is a unique. So it carries out. So we can say that T of Vk plus 1, T of Vk plus 2.
And all bases are
Until-
equal dimensions. So, I mean, what cardinality?
Yeah.
So, finish.
From
How did
exactly.
I
Very
equals
neat.
1 change to I equals k plus 1?
What does what does V1 map to? Under T.
0.
Exactly. So that just cancels out.
Oh, so you don't need to consider it.
Yeah, so like you do
Yeah.
consider it, but it just like goes away. Like that term just goes away. So it is still alpha 1 T1, TV1, and so on up until alpha K TVK. But these terms are all just 0.
Right.
So we have this. So this forms a basis for image of T. And now we're done. So done. Because now we get that dimension of image of T is equal to dimension of V minus dimension of kernel of T. Quite neat. Okay, I am not following the chat for like the past few minutes. If there's something like about what I'm, it doesn't look like it's some interesting discussion about infinite dimensional vector spaces. Okay, sure. Yeah, so this was the Rank-nullity theorem. Okay. And like coming back to this idea of thinking of linear maps as matrices. So the way to do that, think of them as matrices is basically again this idea that you only look at where the elements of the basis are going. So you fix some basis of V and you look at where those things are what these are mapping to. So whatever T of V1 is mapping to, whatever T of Vn is mapping to, you consider that. And based on that you can get any vector. So basically this, if you fix a basis for V, then you are going to get and if you fix a linear map, then that entire linear map can be characterized simply by where the basis elements are going. And if you just make so the nice way to write that is, okay, let's you T of V1 is going to be some so if you've seen this is like multiplication of a matrix and a vector. So T of V1, T of Vn, you just write these are going to be some vectors. T of Vn is going to be some m dimensional vector, because again you can fix some basis for a W and you can write T of V1 as some linear combination of m things. You can write T of V2 as some linear combination of m things, and so on. So, okay, before I go to the representation of matrices, so once you fix a basis for, let's say V, then you can write any vector in V as an n tuple, where n is like the dimension of V. Because let's say any vector in V, let's say the fixed basis is V1 to Vn. This is the basis. Then if V can be written as summation alpha I Vi, then you can just think of V as this tuple alpha 1, alpha 2 up until alpha n. Or as like the vector alpha 1, alpha 2, alpha n in sense in Fn. So in fact, there is an isomorphism. Yeah, this is something I think Shreya mentioned a while back. There's an isomorphism. So it essentially, if isomorphism seems like a fancy word, essentially all we're saying is any vector space of dimension n has is isomorphic is essentially the same as f raised to n. Basically, you can visualize that as n tuples, and that will be the same thing, like vectors of n dimensions. So if there's an isomorphism, V has, let's say, dimension n. Who writes like this again? V dimension n is isomorphic to f raised to n. And this is precisely the isomorphism. Huh?
What's f to the power n? I don't know how to read this.
F to the power n is basically like all n tuples. So like, you know what R to the n is, right?
Yes, vectors.
Same thing.
Nth
Same thing. So F is like some general field. It's the same thing. It doesn't
Okay.
matter. So it's just n tuples, but elements coming from F. So yeah, so these two are essentially the same objects is what we're saying. So yeah, I think that was what I think the discussion in chat a while back was going on about this. So Shreyan was saying, these seem like two neat structures? Is there something complicated? But because of the existence of dimensions, essentially anything with finite dimensions is just equivalent. Or anything you can say, any vector space you can say is equivalent to f raised to something. So that's quite neat. So now you can write V as just like once a basis is fixed, then any vector V, any vector in our vector space can just be thought of as an n tuple. And then so once we fix some basis for V, once we fix some basis for W, then any linear map between V and W can be thought of as a matrix. So what we can do is we can write T of V1 as T of V1 can be written as some m tuple, some m tuple, because it's some element of W. So and W has dimension m. So you can write it as some m tuple. Then you can write T of V2 as some m tuple, and so on up until T of Vn.
If if T is just a pure rotation, is it correct to say the kernel dimension is 0?
Yes, because only the zero vector will map to 0. Otherwise, everything will. Okay, sure. If it's a rotation centered at 0, there's like there will be only. Yes. If it's a rotation, then it's a nice mapping because you don't have multiple things mapping to 0.
Right, because then
The kernel is 0.
what you said m equals n, then the m tuple is
Yes,
just
exactly. So the image of T and the dimension of the image of T, the image of T like is the same as, so V and W would be equal. If it's like rotating, then the space is like the same, right? The space
Right.
remains the same. So these two are
Like T could be
the same.
a mapping from like one projective plane to another, and then you could have what do you say? Image of T as the line joining, like the line going to the light source, passing through the second plane.
I am slightly confused. Wait, how are you defining T? Like us between, why is it between projective spaces? Like T makes sense only between like vector spaces.
But projective
So,
planes can't be vector
sure.
spaces.
Okay, so you're saying you have like two planes.
Projective
You're
planes.
defining, okay. Do they have like the same dimension or something? Like And
Yeah,
then what is
projective
like
plane
the
as
map?
like 2D plane, like projective 2D
2D
plane.
plane. Okay.
So like
It's
you know that
huh.
if you send like it's projective means you are sending some sort of light from some light source and you're getting the second
Huh.
plane from the
Okay, so I think what you're saying is like, I think the way you are imagining this is like you have two different planes and like 3D space. Is that what you're doing?
yes.
Okay, so like what this is, okay, this is not so you're just using vector space, you cannot really differentiate between like two different planes as such. Because they will both be equivalent, just like if you think about them in a okay, maybe like Shreya and Bhairav can also comment more on it. But my understanding is that like if you have two different planes, then like just through the perspective of like if you, no perspective is wrong. What if you're only like restricting them to like vector spaces? Then they are isomorphic to each other. So essentially that ends up being something that is sending like the plane to itself. Something. Or uh,
Okay.
wait, do other people have some comments to make about this? But, yes, Ran. Okay. Yes. Okay. Um, yeah, it's quite weird to think of a linear map as like imagining it in that way, sort of. Okay, I'll try to think about it. Huh.
But a projective plane
What?
can be defined as a vector space or not.
Wait, I forget what exactly. Like, if you're just thinking R2, then sure, it's a vector space.
Yeah, so you could have
But
like two different R2s. Is that even a
oh,
vector?
no, that's the thing, right? Yeah, any two R2s are like isomorphic. I mean, like any two vector spaces with dimension 2 are isomorphic to each other.
Okay.
They're
Wait,
they
but
they are essentially the same structure.
okay, right, kind of. That's true. But the orientation and the like, what if you take two projective planes in the 3D world?
Okay, first of all, I think you are misusing the word projective plane. It is like
Yeah, I
projective
believe
plane
so.
and R2 is not the same thing. Projective plane is something
I get
else.
it. Okay.
Entirely. Yeah. So if you're only considering like two R2s, then like vectors according to vector spacing, both of them are the same thing. There's no difference as such. So like when you're saying you're going from R2 to R, like some two-dimensional thing to some other two-dimensional thing, it's like it's taking the thing to itself. I'm not sure if we can visualize it as like two different planes and then one going to the other, and then doing something of, and I'm not even yeah, wait, or maybe I'm not fully understanding you correctly, probably. Uh, projective plane, no, like projective plane is not something to worry about for now. Projective plane is
Probably my
uh,
definitions are scuffed, I guess.
yeah. Yeah, so yeah, these things, okay, I'll just quickly finish how to do this. Like you can think of T of V1, T of V2 up until uh T of Vn, and you can so you'll get these mn things and you put them in a matrix, you put them in an m by n array or and then you call it a matrix. And then if you want to figure out where some vector in V is going, so firstly you can write it as some n tuple, and then you do the multiplication of this matrix and your vector in V. Like this is exactly how it works if you know matrix and vector multiplication. And also yeah, this other thing I said. about multiplication of matrices is also some. It seems very random when you look at it first, but maybe this is something you can try to figure out for homework. That like composition of two linear maps, and you consider their corresponding matrices, and it turns out that their composition is like the exact same as just multiplying those two matrices. It's quite cool. So also like another point is like again as something we discussed a lot is that okay, anything that has dimension n is just the same as like we can just consider it as an n tuple. So that's why I think in school mostly when you learn linear algebra you really like look at matrices and vectors and stuff, which is all like if you're only looking at least finite dimensional things, this covers all possible vector spaces basically. Yeah, I think that's my time. Okay. Okay, just like a quick recap, maybe we can do what so we started off with the recap for the last class. Then we showed that any two bases have the same cardinality. By the first proof, the ending was slightly wrong, but it's not fully wrong. You can still you can induct on it, and you don't have to explicitly say that their spans are equal. You can induct on the dimension that works. And then this other standard proof also, which is quite neat. And then we looked at the Rank-nullity theorem. By the way, side note, you should go back to the last class and look at the first isomorphism theorem, and you will notice that okay, this directly follows from the first isomorphism theorem as well. And yeah, and then we looked at this expansion of basis idea, and then sort of just like related it with matrices and vectors. Yes, that is all. I hope you learned something new. I think this was fun for me. I had fun. Oh, you were only seeing my forehead. I did not know that, but okay. Yeah, this was quite fun for me. I hope you had some fun and learned something new too. Maybe we'll put up some nice exercise, like compile some nice exercise problems to try after this. Yeah. Maybe in the coming week we will do that. Is there anything else?
Yeah, could you like give some problems for like the network flows one?
Okay, I'll start the record.